So let's continue with the sample size calculation. So there is an unfounded fear among researchers that if you try to calculate how many animals you need for your experiment, statistics will tell you that you need thousands of mice. This is not reality. So reality is that there are five variables that we will call number of samples, relevance or effect size, the variance, and this statistical significance and statistical power that are related. So if you fix four of them, the last one can be calculated. So um, let's the number of the sample size that you need for an experiment, it will have some statistical constraints that are the ones that we will focus on this lecture. So this kind of constraints are what is the what is the comparison that you will do afterwards. So once you have collected your data, you will compare everything to a control group, and you will compare the mean of these two groups, or you will compare the proportion of animals that have a particular feature, or the data is normally distributed or it is not normally distributed. This is the first experiment ever about this topic, so you don't know what is the variability of the observations. So these kind of constraints are the ones we will focus, but there are also experimental constraints. So for instance, you need a minimum amount of material to perform your experiment, or for instance some animals die or disappear from the experiment for any reason before you can measure them, or you cannot handle more than, let's say, 100 mice at a time, 100 or whatever number, it can be 10 or 5, or sometimes the mice move while you're injecting, and then the treatment is not applied in such a good way, so it is partially effective only. So all these other experimental constraints you know better than I do, and these constraints can be taken into account in this in the statistical design. So somehow indirectly, but they can be taken into consideration. So we will see later how. So I will now kind of cartoon a typical situation when people have, researchers have to calculate the sample size. So typical situation is that researchers normally prepare their application to the ethical committee, and then they don't justify the sample size, and then they are returned the application with the comment that the sample size has not been properly justified. But then they go to talk to a statistician, and they come, hey, I have been told that I have to talk to you to write in this form the number of mice that I need for my experiment. I have enough with 3,000. So 3,000 sounds like a lot. So there is a catch. People are not crazy. So yeah, let's see what is the justification behind this 3,000. And what the researcher is thinking is that he hates all this writing for the ethical approval of his experiment. All he cares is doing the experiment and the excitement of research, and see what comes out. And why should he bother talking to a statistician that doesn't know anything about his experiment, biology, anything related to his work? So, okay, you may be right. Now the researcher is happy. You may need fewer animals so that you're losing part of your time, part of your money that you could use to some other experiment. You could use to pay a student, you can use to buy more material, and more importantly, you may save some mice lives. So things that we have to do in research to animals, they are not pleasant to the animals. So it is very important that we use just the number of animals that we really need, not more, not fewer. So let's say that instead of 3,000, you need only 2,000. So 1/3 of the experiment, of the money that you spend on your experiment, could be spent on something else. So yeah, you have lost a bit. But the problem is also that you may need more. So what if instead of 3,000 you need 4,000? Then you have, it is not that you have lost a bit of your money, your time, mice lives, but you have lost all of them, because when you try to compare the groups, the p-values seldom are below the threshold, this 5% threshold, and then at the end you will never be able to show that your treatments are effective. So you have thrown away all the animals for nothing, because at the end there is nothing to compare, and all the comparisons are not above the level of noise, and then you never show that your treatments are effective. So maybe why don't you calculate that? So why don't you calculate? Well, what are you doing? Okay, so I'm studying how the area of a lesion, so this is a cutaneous lesion, changes with a new drug or a new treatment that you are developing. Okay, are there previous experiences about that? This is a kind of textbook answer. Of course, there is no previous experience. This is science. It is novel. What a stupid question. So yeah, talking to this guy was a bad idea actually. Okay, so really, so you don't know if that lesion that you are studying is in the order of 0.1 millimeters squared. Remind that this is an area, or it is 10,000 millimeters squared. So there are 6 orders of magnitude between these two numbers. Actually, the second one is an exaggeration, because that would require several miles to cover all that area. No. Yeah, the lesion, I know the lesion is somewhere around 50 millimeters squared. So now you know one of the means of the control group. So not one of the means. You know the mean of the one of the groups, that is the control group. Okay, so when would you say your drug is interesting? And again, a kind of textbook answer. I don't know. I just want to see what comes out from the experiment. Okay, but for instance, if the drag decreases from 50 to 49.5 millimeters squared, would you say it is worth it? So even if this reduction, this drop, is statistically significant, would you say that the drug is interesting? Because if you have such a weak drug, probably you cannot sell it anywhere. So no, let's say that to be useful, the drug at least has to decrease the area by half. So it should drop from 50 to 25 millimeters squared. So now you know something that is called the effect size. We will refer to it as delta. So this effect size is the gap that you want to detect. In my previous video, we also had a gap. So we had a gap before between 80% of the animals were dying from the infection, and with the new treatment, 0% of the animals were dying from the infection. I don't know if that will happen, but if that gap happens, I want to see it with a given statistical power and confidence level. So this gap is actually the main variable that you can control when calculating the sample size. It is what you want to detect. It will happen or it will not happen. You don't know before doing the experiment. But if it happens, then you will be able to detect it with this confidence level and statistical power. So Yeah, so this is our effect size. This is what I want to detect if it happens. Okay, so now, what fluctuations do you expect around 50 millimeters squared in the control group and in the treatment group? And again, I don't know, this experiment is new. If it is not new, I wouldn't have anything to publish, anything to patent. So, yeah, so I don't know. So, yeah, yes, by the way, what we have defined here, it is the relevance. Now we are talking about the variance. Okay, so you don't know really what fluctuations you have. So you don't know if, for instance, in the control group, you would expect areas that are of this kind. So it is 50, 49.96, 50.14. So all these numbers, they are very close to 50. The average is 50, but they are very, very close to 50. If there is a drop from 50 to 25, I only need one animal to say that treatment has been effective, because there is such a big change in terms of the fluctuations that I normally see in the control, that this fluctuation, this drop, cannot be caused simply by chance in the control group. But on the other side, I could have a control group whose measurements look more like this. So we have 58, we have 8, we have almost 32, 22. So the average, again, the average of these numbers is 50. But now detecting a drop from 50 to 25, it's much more difficult because the numbers fluctuate much more. Even in the control group, there are two animals that are already below 25. So we have an animal with 8, we have an animal with almost 22. So it could be that just by chance my treatment is not effective, but I have responses in the two groups. Let's say that in one of the groups I have one of these big numbers, so like 58, 31, 129, and in the other group the treatment is not effective, but just by chance they concentrate all these animals with lower responses. So if my sample is too small, this might happen. So I will need a larger sample size to be able to protect myself against this random grouping. So it is much more difficult to detect a change from 50 to 25 if this is the fluctuation than if this is the fluctuation. With this one, I just need one animal. With this one, we will see that we need around 30 animals. So, and this highlights something of the sample size calculation. Actually, when you're doing a comparison between groups, what you want to detect is that this change that I see between the two groups is above the level of noise. This is defining the level of noise. So the level of noise is given by the variance of your observations that we already saw at the beginning in the first video, that this variance is caused by the biological variability plus the measurement noise. Okay, so I don't know what is the fluctuations that I have. So some people are really stubborn about this. So okay, so if you really don't know anything, then there is no other way than doing an exploratory experiment. Then you measure what is the variability with a few animals, and then you will design your experiment again. And this has implications in terms of how many applications you have to do to the ethical committee. So people don't like this idea of making exploratory experiments. Actually, there is something that comes out from exploratory experiments. They're typically done with very few animals, 4 or 5 animals, and with this low number of animals, the variability that you observe in your experiment is there is a lot of uncertainty about that variability. So the true variability could be 3 times larger than the one you have observed, or it can be even 3 times smaller. So 3 times up, 3 times down makes almost an order of magnitude in uncertainty. So probably you get the same amount of information if you read a paper that uses the same kind of animals, at least for the controls, and then you measuring the numbers from that paper, you get a good idea of what is the variability that you should expect. And if this is the first experiment ever about this kind of measurements that you're doing, there is no other way than measuring a few animals. I like to make the analogy. Let's say that you are asked to design an elevator for aliens, and you want to put in this elevator to be such that 10 aliens can go up and down. But if you have never ever seen an alien, how can you design an elevator for 10 aliens? So there is no other way than going uh, to see some aliens. Now, once you have seen a few of them, now you can design the elevator. And mice, in many respects, are not aliens. So they have been studied a lot of times from many different aspects. So maybe the specific response of a gene is completely new, but then you will have to fetch a few aliens and measure them. Okay, well, there is a paper where they do something similar to my experiment, but with a different drug, and they report a variance of 1,000. So, as we said before, the control groups typically they are shared between experiments. So the control groups of this kind of lesions, they have been studied multiple times, but with different drugs. So the treatments are different, but the controls are more or less the same. So they report the variance of 1,000. So this variance is more like this one. So we have very variable observations. And for the treatment, it is true, the treatment is new, so it is less clear, but we may assume that we will have similar fluctuations. They cannot be too far from the fluctuations, the kind of fluctuations that we see in the control group. Actually, we can refine this statement. So, for instance, if you are observing a decrease in the lesion area, normally the variance also decreases. And if you are seeing an increase in, I don't know, the concentration of some metabolite in blood, then the variance also increases. So it goes, the variance decrease or increase goes with the sign of the increase or decrease of what you are measuring. Okay, but let's say that it is the same. So let's say that it is the same. So now you have the variance for both groups. And if you're not sure about the treatment variance, you may also apply some safety factor. So it is like when you design elevators, so you put some safety factor on the weight. So you say, okay, 20% or 30% more variance in one of the groups. Okay, so let's say 20% is fine. So now you have two groups with different variances. And well, and you know later when you do your experiment, you will compare the control group to the treatment group. So it could be that you decide that the treatment is effective when actually it was not. So this is called a false positive, or a type 1 error, more technically. And how likely you want to make these errors. So how often you want that the treatment is not effective, but because of bad luck with your samples, you think that it is effective. And this typically has been chosen to 5%. And that is your confidence level. So 1 minus 5% is your confidence level, so it is this 95%. And this 5% has been reported so many times in papers that no one argues. There is nothing special about 5%, so simply tradition. And even there is now a movement in science that promotes using rather 1% than 5%. And the reasoning is that if you think 5% is 1 in 20, so let's say that in 20 experiments in which there is no difference between the two groups, one every 20 experiments you will think that there is a difference. So that probability is too high, probably, especially now that we are doing so many experiments. So some people promote that to increase the reproducibility in science and to avoid reporting incorrect conclusions from the experiments, this probability should be lowered to 1%. Okay, so yeah, 5% is quite a standard, so no one argues that. Okay, so there is also another danger, that is missing good treatments. So maybe you are unlucky again with your samples, and an ineffective treatment, you think it is not effective simply because you were unlucky with your samples. This is called a false negative. So negative because you think that the treatment is not effective, but actually it was. Or they are also called type 2 errors. So how likely you want this to be? So you may choose something like 10-20%. So you can also choose 5% if you want. The more the less likely you want this event to be, the more animals you will need. And the statistical power is defined as 1 minus that probability. So if the probability is called beta, that is typically 10, 20%, 5%, 1 minus beta will be the statistical power. So statistical power is very important. So let's say that you have very little statistical power. So you have only 10% of statistical power. So that means that in 90%, that is that is beta. So beta is 0.9, 1 minus beta is 0.1. So that means that in 90% of the cases in which the treatment is effective, you declare it to be non-effective. The p-value is seldom below the 5% threshold. So for that, I wouldn't do any experiment, because any time that the treatment is effective, I do my comparison, and then I never say that there is a difference. So for that, there is no point in doing the experiment. So you don't want the statistical power to be very low either. So you want it to be sufficiently powerful, and sufficiently powerful translates into enough animals or enough sample size. Okay, so you want to be very sensitive, so you choose beta equals 0.1, and now you have everything. So we have set the relevance, that is this gap that we want to detect. We have we know what is the variance, so what is the fluctuations that we expect in each one of the groups, and we have fixed these two probabilities of making false positives or false negatives. So we may make the two groups to have the same sample size, and this will be n, and the n depends on a term that depends on the confidence level, a term that depends on the statistical power, and a term that depends on the gap that you want to detect, and the variability. And the dependence is quadratic on these two terms, and linear in this one. And yeah, it looks complicated. Actually, it is the simplest formula that you can have. Actually, it is an incorrect formula, but it conveys the right ideas. So for instance, if you want to have more confidence or more statistical power, these two terms will be larger, and then the n will grow, and it will grow quadratically with this confidence level and statistical power. If there is more noise, then your sample size will also need to be larger. And if you want to be more sensitive, so that to detect smaller gaps, so the smaller the gap that you want to detect, the larger the sample size. So it goes in the right way. But yeah, you don't have to do these calculations by yourself. So a long time ago, I was providing people with an Excel sheet where they could make these calculations. But later we shifted to some programs, GPower, that we will use during this presentation. It allows to calculate this sample size, and actually this representation here is the correct way of doing the calculations, right? It's much more involved. So the thing is that at some point when you are comparing the two groups, you will compute a statistic that is called the t-student statistic. The specific statistic that you compute depends on the comparison that you do. But in this calculation between two groups, the mean of two groups, it is the t-student. So if the null hypothesis is true, that is, if there is no difference between the two groups, this is the expected distribution. This is the expected distribution of the t-student. And if there is a difference, then for instance, one of the groups, the response is larger than the other group, then the t-student will shift to the right, and there will be a critical value. This critical value, if your t value, the statistic that you have found in your experiment, is beyond this critical value, you will reject the null hypothesis. And if it is smaller than this critical value, you will not reject it. And the probability that you reject the null hypothesis when the null hypothesis is true is this area, this red area here, that is alpha. This is the how likely you want to make false positives, and the likelihood that if the alternative is true, you don't reject the null hypothesis is this area, this blue area here, that is beta, that is this the one that is related to the false negatives. So actually the calculations have to be done through these distributions. We will see them later with the GPower, but some simplified form is this one, and it goes more or less in the right direction. So the trends that we have described for this formula, they're also met by these kind of analysis. This kind of analysis is called power analysis. Okay, so now, good news, you don't need 3000, you need only 31 mice per group, so not 3000. Okay, but you know, sometimes some mice get cold or die, or they fight each other, or for any reason I cannot measure them, and then if I need 31 and if I lose a few of them, I will not have 31 anymore. So how often does it happen? Okay, so it happens 20% of the times. This is what I referred to at the beginning of this lecture, that if there are experimental constraints, you can put them into the equation. So for instance, if there are dropouts, you can increase the sample size such that when the data drops out, still you have 31. So if you expect that 20% of the data will be useless, then you, instead of 31, you put 39. So 39, the 80% of 39 is 31. So this is this calculation here. So still, if 20% of the data drops, then still you will have 31 samples to make your statistical comparison. And this researcher also wants to test several drugs. Actually, this is what I meant at the beginning. People are not crazy. So if they need 31, they don't use 3000 for just for nothing. So when you do the application to the ethical committee, you don't do the application for one experiment, but for the experiments in the next 3 years. So in the next 3 years, you will try multiple compounds, multiple vehicles, multiple doses. So these multiple experiments is what justifies the 3000. But the point is that you have to show in the application that you know how to calculate the sample size in each one of the experiments that you will do in the next 3 years. So yeah, one of the points is that if you will do multiple experiments, let's say that you will do M experiments along your along these 3 years, it is better to reduce the alpha, because otherwise we will have this increase of false positive rate that we talked at some moment before. So this 1 in 20 or 1 in 100. So you will because you are doing many experiments, you want this probability family-wise to be still low. So we will see it later in the next video, but there is an increase by making multiple comparisons, by making multiple tests. The number of false positives increases quite a lot. So yeah, it is better if you're doing M comparisons, instead of using alpha, you use alpha divided by M. So if you will do 100 experiments, instead of using 5%, you use 5% divided by 100. Okay, this is, by the way, is called the Bonferroni correction. That is very easy to apply, and you may have heard of. Okay, so what happens if I get an unreasonable number of mice? So let's say that this 39 per group, this is still too high. So you will have to change something. So typically statistical significance and power, you don't want to change. Significance, because if you put it too low, you will never be able to publish anything. And the statistical power, we already reasoned that if it is too low, for that we don't do any experiment. So this you cannot touch much. The variance also you cannot touch much. We have talked a bit about decreasing it a bit through the technical replicates, but sometimes that's not possible. So if the noise variance is not too large with respect to the biological one, there is no point in doing technical replicates. And we have also discussed that actually the variance that you have to put here, it is the variance that is unexplained. So that is why explaining variance, part of the variability through sex, through age, it is so important, because the variance here for the sample size is the unexplained variance. So if you can identify blocks that can induce variance or explain part of the variance, the better. But there is a limit again. So if once you have used all these tricks, like blocks, technical replicates, and so on, the only thing that you can change is the relevance. So let's say that 39 is a lot. So 39 was to detect a change of 25. So that is n. 39 is a lot. So you will have to increase your gap. So you will have to increase the change in signal above the level of noise, so that it is easier to detect. So instead of dropping 25, it will have to drop, I don't know, 45. So it is almost cured. So either your treatment almost cures the lesion, or you will not be able to show that this decrease is above the level of noise. So actually the one variable that you can really touch is the relevance. What do you want to detect? Also, some researchers think that they have to replicate their experiment 3 times to be statistically significant. And there are two aspects here. So one is bias, the other one is variance. So let's say that there is a true gap between the two groups. So let's say that in reality this gap is 25. You measure it once with two groups and you don't get exactly 25. So you measure it once and you get 24, let's say. You measure it again, you get now you get 25. You measure it again, and now you get 26. So the average of all those gaps is 25. So there is a very little variability around this 25. So this is what you would like to have. So you would like to have low variance, so that the variability around the 25 is low, and low bias. Low bias means that if you average all your estimates of what the gap is, you get the true gap. Could be worse, could be that there is more variance. So instead of 24, 25, 26, you get much more variability. You get, let's say, 20, 25, and 30. Still the mean is 25, that is the true gap, but observations are much more variable. So this more variability is very well handled by all these statistical tools, p-value, confidence intervals, and these kind of things. They really handle well variance. But you could have bias. So bias means that you get an incorrect estimate of the gap size. So you could have low variance. So let's say that the true gap is 25, but every time you try to measure, you only get 10. And you still have low variance, so you have 9, 10, 11, so very numbers that are very close to 10, but the average of those numbers, that is 10, is far from the truth. So let's say that the truth is here, that is 25, but you get something that is far from the truth. So that is bias. And you might have multiple sources of bias. So let's say that you systematically applying correctly the treatment, or that systematically you are using a pipette, and this pipette, you think you are applying 1 milliliter, and actually the pipette is miscalibrated, and you are applying all the time 0.5 milliliters, or there is I don't know, some analytical measurement and the machine is uncalibrated, and again systematically you get incorrect measurements. So there is no way that the statistics can tell you what the reason of the bias is. There are some ways of estimating the bias. That is actually what this replication of the experiment by 3 times is trying to identify. So we have two sources. One is bias, the other one is variance. So in terms of variance, if there is no bias, so repeating the experiment or not depends on what is the p-value. So if the p-value is 10 to the minus 15, it doesn't matter how many times you repeat your experiment. You will always see a difference between the two groups. So something that we don't realize is the p-value in itself is a random variable, so it fluctuates also. So if you repeat the same experiment with the same kind of response, sometimes you get a p-value, some other times you get another p-value, so that is randomness. So this randomness in the logarithmic space, it can range for 3 orders of magnitude. So if sometimes you get 10 to the minus 15, some other times you get 10 to the minus 12, some other times you get 10 to the minus 18. So so there is 6 orders of magnitude between minimum and maximum, but still all the time there is a significant difference. The problem is when the p-value is close to the threshold. So if it is close to 0.05, that is this 5% threshold to declare something significant, sometimes because of this fluctuation of the p-value, sometimes it goes below the p-value, the threshold, sometimes it goes above the threshold. Actually, if the p-value, let's say it is 0.04999999, so if you repeat the experiment, there is a chance that because of the fluctuations of the p-value, you were just below the threshold. Now you are just above the threshold. So actually, if the p-value is alpha, there is a 50% chance of falling on each side of the threshold. So repeating the experiment because of the variance depends on the p-value. So if the p-value is very low, there is no point in repeating. If the p-value is close to the threshold, then there is a good point in repeating it. And about bias. So about bias, you can, if you do your experiment only once, how do you know that the pipette was not miscalibrated? You can never know. So that's why repeating the experiment is a good thing, it's a good idea. But actually there is an even better idea. So here is the, so this is our sample size of 39 that this researcher wants to repeat 3 times to make sure that there is no bias. But actually there is an even smarter choice. So instead of repeating 3 times, you can split the experiment in 3 mini experiments. So now you do in 3 weeks. So you do a mini experiment with 13, another mini experiment with 13, and another one. So yeah, there are some technicalities of there is no free lunch. So if you are splitting your experiment in 3 weeks, you will have to estimate what is the contribution of each one of the weeks. But that is what I'm representing here with the degrees of freedom and so on. But the idea is that if, let's say that the pipette was miscalibrated in the first week, but because of this randomization we were talking before, now you use a different pipette for week 2 and a different one for week 3. So it is very unlikely that the 3 of them are miscalibrated. So that means that by dividing the experiment in 3 mini experiments, you will be able to detect that the response in these 2 weeks are much more similar to each other than the response in the first week. So in the first week there was something wrong, and that doesn't mean even that you have to throw away your first week. So the results of the first week, because of you have split it into blocks. Actually the week is a block. So you see that we have a block and we see the 2 treatments, the control and the treatment in that block. So because of this balanced design, we will be able to estimate what is the contribution of the week, what is the contribution of the block. There is some reason, I don't know if it is the pipette, if it is the machine, if it is the researcher, I don't know what it is, but there was a bias in week 1 that didn't happen in the other 2 weeks. So that is why also randomizing is so important, because if you use the same pipette for the 3 weeks, then there is no way that the statistics can tell you, okay, the pipette was miscalibrated. So you see the same response in the 3 blocks. But instead of doing the experiment 3 times, it is much more intelligent to do 3 mini experiments with a smaller sample size. So in summary, following this methodology makes you think of what is reasonable to expect from an experiment. So if you want to detect a gap of 25, you will need 39 animals. If 39 is a lot and you can only work with 8, now you know that instead of detecting gaps of 25, I will be able to detect much larger gaps. And now you know what to expect from the experiment, and you know what is the balance that you have chosen between sensitivity, this effect size that I'm able to detect, the errors, these false positives and false negatives, the sample size. So you know what is the balance that you have what is the trade-off that you have chosen among all these variables. And you also know how many mice you need for the statistical test, how many animals you have to increase because of the dropouts and experimental aspects, or these experimental aspects may put a limit on the number of animals that you can use. So you know all this balance and this trade-off, and so you know much more about your experiment before doing the experiment, and what you are guaranteed is to save money, to save time, and to save mice lives that are of primary importance. So after all, following this methodology is not so bad. Okay, so let's stop here, and we'll continue next with some more considerations about this methodology.